welcome back to this NPTEL lecture. Let me switch the gear from tribological studies of bioceramics and composites to fretting and wear properties of other non-oxide ceramics, Sialon oxide, Sialon ceramics. Although Sialon ceramics can be used for biomedical applications, there is a company based in US who used to develop the silicon nitride ceramics for biomedical applications, but however, it has not penetrated so far very deeply into the biomedical device industry, and I am not aware of too many companies who are developing silicon aluminum oxynitride based materials for biomedical applications. Therefore, I would safely consider silicon aluminum oxynitride based materials as an important class of ceramic materials which are currently being used for many of the structural applications and engineering applications, but certainly not for biomedical applications. Now, what is silicon aluminum oxynitride? Those who are not from ceramics background, most of you know that silicon nitride Si3N4 is one of the popular ceramic materials, but alumina is a kind of a model ceramic materials. Now, silicon nitride can form solid solution when you use alumina, aluminum nitride and silica, and if you form this 4 component system, then the solid solution that form, so it is called silicon aluminum oxynitride. So, silicon aluminum oxynitride is essentially a solid solution of silicon nitride with other oxide or nitride phases. So, those who are from metallurgy background, they know any material when exists in the solid solution phase, typically it has better mechanical properties, better hardness, better strength properties. A popular solid solution alloy is steel. Steel is a solid solution of iron and carbon. If there is no carbon, you cannot call it a steel, it is a pure iron. So, similarly, and why steel? Because steel has pure iron is very soft, but when you have carbon in the solid solution with iron, certainly that steel has a better hardness and strength properties. Now, in line with the similar argument, in case of the ceramic alloys like silicon aluminum oxynitride also has better strength and better fracture toughness properties than silicon nitride. So, therefore, in this particular case study, we will try to see that, so whether we can measure this wear resistance properties, how the wear resistance properties also depend on the microstructure of this material. So, these wear resistance properties mostly are measured using the Sialon as a ball. So, essentially we are discussing here self mated couple like Sialon against Sialon balls, and then load that we have chosen, it is around 8 Newton. This relative displacement at the contact is 100 micron, 6 hertz is the frequency, and typically 45,000 is the cycles. Now, silicon aluminum oxynitride materials also there are 2 polymorphs, one is that beta Sialon and the one is alpha Sialon, and beta Sialon and alpha Sialon is in line with the same argument, because baseline material, that is silicon nitride, they also have 2 polymers, alpha silicon nitride and beta silicon nitride. So, similarly alpha Sialon and beta Sialon ceramics, they have not that both of them have similar properties. For example, beta Sialon has good sinterability and relatively high fracture toughness, and these are associated with the rod like grains. Alpha Sialon on the other hand has higher hardness, but their sintered microstructure typically composed of the equiax grains. Now, this is the typical this is little bit more details of the alpha Sialon and beta Sialon based materials. So, you have that initial silicon nitride powders, alpha silicon nitride, which is a typical composition of Si 11.5, N15, oxygen 0.5, and it has also higher reactivity than beta silicon nitride. It is clearly an unstable phase. It is higher solubility than beta silicon nitride, whereas in case of beta silicon nitride, it has a chemical formula as Si3N4, that is stoichiometric formula. It has anisotropic growth rates due to crystal form. This anisotropic growth you can see very clearly. This is your basal plane of the hexagonal crystal, right, and this is your this is the anisotropic growth rate here. This is your prism plane of 210 and basal plane of 0001 plane. So, along C axis you have a interface reaction controlled grain growth, and along A axis you have a diffusion controlled grain growth, and you have a difference in that surface energy, like gamma is decreased along this direction, it is smooth, but in the top basal plane, because it is a rough surface, it has more interfacial energy. And compared to alpha silicon nitride, that is the counterpart, it has a lower reactivity and more stable, and it is a stable phase after 1410 degrees Celsius. Now, in this beta silicon nitride or elongated beta sialon grains, there are different, by changing the composition of the starting powders, essentially you can get different phase fractions in these particular silicon aluminum oxynitride phases or sialon phases. What you see in the bright contrast, these are like residual glass phases, and some of the cases you will see that there is elongated crystals. So, these are the elongated beta silicon nitride beta sialon grains. So, essentially the microstructure is composed of residual glass phases and also elongated beta sialon grains, and these elongated beta sialon grains are very important because these beta sialon grains, they have the potential to reduce the crack growth resistance on the fracture surfaces, and if the crack growth resistance is reduced, then what would happen, that this particular microstructure may have better fracture resistance properties as well. Okay. Now, if you look at this particular table, let me spend little more time. Now, what I am trying to emphasize here, again those for the non-ceramic background people, there are two things. One is that starting powders composition, and one is the sintering conditions, sintering temperature, time, and so on. By changing these two parameters like starting powder, sintering temperature, and time, it is possible to obtain a range of different microstructures. Thereby, one can also obtain a range of properties in terms of hardness properties, in terms of fracture toughness properties, and so on. So, here is the example for ease of comparison. I have specified is as SN1 to SN6 or some different grades, and then we have used that ube powder, that is Japanese powder of silicon nitride, which is a D50, that is that average particle sizes. So, D50 essentially is average particle sizes of around 0.5 micron, and if you sinter them at 1940 degrees Celsius for 2 hours at 22 bar nitrogen. Remember, in the silicon nitride case, one has to use the nitrogen as an atmosphere. Why nitrogen atmosphere? If you use the normal ambient conditions air, then all the silicon nitride will be oxidized to silica. Okay. Now, if you use the nitrogen atmosphere, then what would happen? Silicon nitride decomposition also can be prevented, and oxidation of silicon nitride to silica, that can be also well prevented. And these sintering conditions, as you can see, this is quite an extreme, because 1940 degrees Celsius it is quite a high sintering temperature. If you compare that of alumina, alumina can be sintered typically at 1600 degrees Celsius for 2 hours or 4 hours. If you remember that of the zirconia, I have mentioned in the case study on zirconia that zirconia sintering temperature is somewhere around 1450 degrees Celsius. So, compared to oxide ceramics like alumina or zirconia, typically non-oxide ceramics like silicon nitride or silicon carbide, they require higher sintering temperature for their full consolidation or full densification. So, simply because of the fact that these materials they have very poor self diffusion coefficient, and it is the diffusional mass transport which leads to sintering or consolidation of the powder compact. So, if the self diffusion coefficient is very low, these materials these powders you cannot be densified or consolidated in the, to full density. Now, what is the hardness of these materials? This hardness of this material Cialon phases, that is this materials, this has a this first material SN1, it has hardness of around 16.1 gigapascal. If you go to SN2, that is a different source of the powder where D50 is 1 micron, it has around 15.8 gigapascal. If you go to third one is a beta, it is 14 gigapascal. If you go to SN5, which is a mixture of beta with certain seed of the beta nitride, it is 12.4 gigapascal. And if you go to simple beta, but at different sintering conditions 1850 versus 1940, 1851 hour, then also you get the hardness of 13.2 gigapascal. So, same material there is a difference is around 1 gigapascal. If you see their fracture toughness, which is typically measured using the indentation cracking method in case of the ceramics, you can vary not only the hardness properties, but also you can vary the fracture toughness of these materials. Now, what you have seen in one of the earlier lectures by me, I have categorically emphasized that fracture toughness of zirconia needs to be tailored in order to optimize the wear resistance property. In other words, the major message of that particular lecture was that you can always strive towards obtaining better and better wear resistance better and better crack growth resistance property or fracture toughness properties, but at the expense of reduction in the wear resistance property. So, therefore, one has to have a compromise between fracture toughness and wear resistance property. This is fairly important for you to remember. Now, in this particular case study, I would once again highlight that how fracture toughness properties play an important role in determining wear resistance properties for a different class of materials, that is called oxynitride ceramics like silicon oxynitride ceramics like Cialon silicon aluminum oxynitride ceramics. So, this is again another example of the high toughness ceramics. Typically, fracture toughness of ceramics is varying somewhere between 3 to 4 like alumina and many other silicon carbide, but here silicon oxynitride one can go to as high as 5.5 or 5.6 MPa square root meter, which is close to that of the double of that alumina based ceramics. So, therefore, in ceramic community 6 MPa square root meter or 10 MPa square root meter is a respectable number as far as the fracture toughness of these materials are concerned. So, I reiterate my earlier statement, by tuning or by tailoring the sintering temperature and time as well as starting powder composition, one can get a range of fracture toughness values in this particular set of silicon aluminum oxynitride materials. And this fracture toughness is largely due to the differences in the fracture toughness is largely due to differences in the phase composition, phase assemblage. Now, if you compare these two columns, my statement will be can be clarified. For example, here you can see that beta to alpha ratio is 67 to 33, that is 2:1. Here you can see beta to alpha ratio is 76 to 24, that means more or less 3:1. Here you can get beta to alpha ratio is 92 to bit 8. So, that means again it is more than close to 12:1. Here it is 16 to 84 like 5:1. This is 100% beta. So, when you have 100% beta, here again is 100% beta, you can see that these materials have little bit higher fracture toughness, but also here beta fraction is higher 2:1. Here again one has obtained 5.6 gigapascal. But if it is 100% beta, then you can get better fracture toughness properties, but hardness is lower. But if you have to get a good combination of fracture toughness and hardness, then you should go for this 2:1, like you need to have some alpha phase as well as beta phase, because if you remember in one of the earlier slides in this lecture, I have emphasized that alpha and beta, there are distinct differences, like beta phase or beta silicon nitride or beta sialon phase, they typically have higher fracture toughness, whereas alpha sialon or alpha silicon nitride, they typically have higher hardness. So, that is being reflected here. If you have predominantly beta phase with little bit of alpha phase, then one can clearly have the best combination of fracture toughness and hardness. But if you have pure beta phase or 100% beta phase, then it is possible that your fracture toughness still remain higher. However, because of the absence of alpha phase in the microstructure, you can expect lower hardness properties, and this statement is very well proven in this particular example for the ceramic grades like SN5 and SN6. Now, with this background on the materials, let me now explain that how wear rate is varied with respect to hardness and the fracture toughness of these materials. And what I am going to show you now, that first in case of hardness properties, wear rate typically decreases with increase in hardness properties, increase in hardness of the sialon. So, these are the grades of the different sialon that I have mentioned. So, there are two type of circles. One circle you can see that within the narrow range of 12.5 to 13.5 gigapascal hardness variation, there is a decrease in the wear rate, but this wear rate decrease is not that significant. But if you look at this another circle, larger circle of variation here, this when the hardness is decreases somewhere around 13 or 14 to 18 gigapascal, then there is also a decrease in the wear rate from 8 into 10 to the power minus 5 to somewhere around 1 or less than 1 into 10 to the power minus 5. So, that means there is couple of times reduction in the wear rate of these compositionally tailored sialon materials. Now, so the major message from this plot is that if hardness increases, wear rate decreases, or in other words wear resistance increases. Now, let us now look at very closely how does this wear rate decreases, how this wear rate varies with fracture toughness, which is again measured by indentation cracking, which I have explained to you earlier, but let me explain again. This is the Vickers hardness. In case of brittle materials like ceramic, from the indent corners these cracks will generate and then they will propagate. And if you measure the crack length and this crack length, based on the crack length and based on this diagonal, you can measure the fracture toughness or Kc values is some eta parameter E by h to the power half, then P by C to the power 3 by 2. So, C is your half of the crack length, H is your hardness. So, this hardness is to be measured at a indent load where there is absolutely no cracking. So, indent load where you are measuring the fracture toughness, you cannot use the same hardness value and plug in this particular equation to get the reliable fracture or get the fracture toughness values. So, this is Kc, Kc stands for critical crack tip stress intensity factor. Many times people use this as a K1C, which is wrong, because 1 means this is the critical crack tip stress intensity factor under mode 1 loading. But these indentation cracking methods to measure the fracture toughness does not involve purely mode 1 type of loading, what people can achieve by single edge V-notch beam kind of techniques, where there will be at the crack tip purely tensile loading. But that is not the case in this particular scenario. Therefore, it is appropriate to mention is the Kc, it is the eta E by h to the power half and p by c to the power 3 by 2. So, what you notice here, that with increase in the fracture toughness from around 3.5 to around 6.5 MPa square root meter, your wear rate is reduced from 5 to less than 1 MPa square root meter. So, with increase in the fracture toughness for a specific group of silicon oxynitride ceramics, one can clearly see there is a reduction in the wear rate with increasing in the fracture toughness. So, what it means that since this particular case, and we will see now in the SEM images, in scenario where wear or material removal is dominated by cracking and cracking induced spalling, then if you use materials with higher fracture toughness or higher crack growth resistance properties, therefore, there it is possible to achieve better wear resistance, simply because in higher fracture toughness materials one will have difficulty, or the cracks will find it more difficult to propagate in the microstructure, leading to spalling. So, therefore, crack growth induced spalling can be minimized, and therefore, materials with better fracture resistance or better fracture resistance will be useful for better wear resistance property as well. Now, let me substantiate my statement further. Now, if you look at this wound surface image, the way I am tracing, so these are the typical cracking, right, and this cracking is typically at perpendicular to that of the fretting directions, and you can clearly see there is a thick tribolayer, and then thickness can be confirmed from the contrast difference between the wound surface as well as this tribolayer, and this you are seeing from the middle of this wound surface, and this is how this tribolayer is formed. Now, at different SN4, for example, which is very high wear resistance, very high wear rate, but low wear resistance, this is the scenario. In the SN5, which is somewhere here, where the material has this is this one and this is this one. SN5 is the material where you can see that there is tribolayer, this is a cracking, but tribolayer seems to protect the materials quite nicely, and that you can see from the center of the wound surface. So, what you notice here, that crack growth resistance is increased, as a result the wear resistance also increased. Now, in next few minutes I am going to show you another class of materials, and this class of materials is called S-Sialon materials, S silicon aluminum oxynitride materials. This is a S phase Sialon. You already know there are two phases, alpha phase and beta phase, and then we have already mentioned that non-oxide ceramic like silicon nitride, they have high fracture toughness and high temperature strength, which is not the case for silicon carbide for oxide ceramics. So, therefore, non-oxide ceramics are very important for various engineering applications. Okay. So, non-oxide ceramics are very important, and then you can do this silicon, part of the silicon in the silicon nitride lattice is replaced by aluminum, and part of the nitrogen replaced by oxygen, then you form the Sialons. So, in 1999, almost like 20 years ago, Jean Sain's group at Sweden, I think Stockholm, they have discovered Sialon is a new phase, that is S phase Sialon, which is a composition of M2 ALX Si 12 minus X, nitrogen 16 minus X and O2 plus X. and with X is equal to 2 and M is a cation of group 3 or group 2 of the periodic table. A larger cation barium to strontium substitutes some part of the aluminum to silicon, and that influences the material properties. How these materials are done, how these materials are processed? As I have mentioned earlier, that Sialon materials you use that silicon nitride, aluminum nitride, alumina. So, all these phases are same, but to dope with barium, it is we have to use barium or strontium, we have to use the precursor powders, that is barium or strontium carbonate. You mix it, you dry it, you hot press this dried powder mix at 16 to 1750 degrees Celsius. You can do alternatively pressureless sintered. So, it is or pressureless sintered at 1750 degrees Celsius, then you get barium, strontium, silicon, oxygen, nitrogen. So, that is the barium or strontium variation of the Sialon family. This is the typical XRD traces, and what you notice here that you have a barium doped S phase, silicon S Sialon phase. This is that phase pure, and also there is one more phase called beta silicon nitride, but their amount is certainly much less, because barium based S Sialon phase is very significant amount. So, typically beta phase silicon nitride, it is a typical needle that which is dispersed in the microstructure. You have the residual glass phase and you have the barium doped S Sialon phase, which you can clearly see is a very fascinating microstructure. This is a tabular shaped barium silicon aluminum oxynitride phase, and you can see that barium silicon oxynitride phase. If you take a EDAX spectra, you can in TM you can clearly see the composition that strontium barium peak. So, you have that typical tube shaped or latch shaped materials, and then you can see also this is a different magnification. So, typically the width of this tabular faces parallel to the 0 1 0 plane, it is around some 400 to 500 nanometer, and also there is a definite aspect ratio of this phase, and this aspect ratio is somewhere 8 to 9 aspect ratio. We can see very clearly that there is threads of dislocations. So, these are defect structure, and somewhere also we have seen APB antiphase boundaries that there is dislocation threads in these particular ceramic materials. So, as far as the properties are concerned, it is not a great property in terms of the hardness and fracture toughness, because in the last few slides I have shown that by using the different starting powders and hot pressing conditions or sintering conditions, one can obtain the fracture toughness and hardness over a large range, and this is somewhere in the middle. So, here it is around 4.5 MPa square root meter, which is not too bad, but at the same time this materials has a steel like elastic modulus like 210 gigapascal. Now, whenever a new material is being tested for wear resistance property, it is always recommended to use 3 different kind of matting solids. Like here we have used steel, Sialon and alumina. So, this is the case for this against steel based materials. This is the case for against alumina based materials. So, first let me explain that how does this wear rate varies. For Sialon versus alumina, this total wear rate. So, total wear rate of the system, it is significantly lowest here. In case of alumina, it is very high here in case of steel, and for self mated couple like Sialon versus Sialon, that is wear rate is moderate or intermediate between that of steel and alumina. As far as the wear resistance is concerned, what you see here that in case of steel materials there is a very thick tribal layer, and there is also delamination wear, and this particular tribal layer is pulled off, and this is your fretted wear surface. So, this is your fretting directions. In case of alumina, there is abrasive scratches, and also there is a deeper abrasive group. So, these are like called groups, abrasive groups, which are present on this wound surface, and then we have a very clear fretted scar on this particular materials. Now, these are some of the 2D surface profiles just to show that how the surfaces the depth of these 2D surfaces, which is fairly good, like around 10 micron, and in some cases depth is less around less than 10 micron also we have observed. So, all these properties we have published in Journal of American Ceramic Society papers in 2007, more than 10 years ago, and this particular ceramic is being investigated in other research groups as well for their various potential engineering applications. Thank you.